Today, we're exploring the terrifying reality of reaching Pluto and the nearest star beyond our solar system. What seems close in space is almost impossible for humanity to reach. This journey will reveal the true scale of the universe and the limits of human technology, and by the end you may realize humanity is far more trapped than we imagined. Now let's begin. 9 years, 5 months. That is how long it took the fastest spacecraft humanity has ever built to reach Pluto. New Horizons left Earth in January of 2006. It flew at 58,000 kilometers per hour, 15 times faster than a rifle bullet. 15 times. A bullet fired from a military sniper rifle would need over 600 years to cover the same distance. New Horizons did it in less than a decade. And still, it took 9 years and 5 months. There was no shortcut. There was no faster route. Engineers calculated every possible trajectory, every gravitational assist, every ounce of velocity they could extract from the laws of physics. And the answer the universe gave back was 9 years and 5 months. Take it or leave it. Let that settle for a moment. The average distance between Earth and Pluto is 5.9 billion kilometers. Not 5.9 million, not 5.900 million, 5.9 billion. If someone got into a car right now and drove without stopping, without sleeping, without ever pulling over at 100 kilometers per hour, 24 hours a day, 365 days a year, that drive would take 6,700 years. The Roman Empire rose and collapsed in less time. Christianity went from a small sect in Jerusalem to the dominant religion of the Western world in less time. The entire span of ancient Egyptian civilization from the first pharaoh to Cleopatra fits inside that drive with centuries to spare. 6,700 years of continuous driving, and you would finally arrive at a frozen dwarf planet that gets so little sunlight. Its surface temperature sits at negative 223 degrees Celsius. And here is the part that genuinely breaks the brain. When New Horizons finally reached Pluto in July of 2015, it sent a signal back to Earth, a radio signal. That signal traveled at the speed of light, 299,792 kilometers per second, the absolute speed limit of the universe, the fastest that anything, anywhere, under any circumstances can ever move, not a speed record waiting to be broken, a hard wall built into the fabric of reality itself. And even then, that signal took 4.5 hours to arrive back at the receivers on Earth. 4.5 hours at the speed of light just to cross the gap between a spacecraft and its home planet. Engineers sitting at mission control in the Applied Physics Laboratory in Maryland had to wait 4.5 hours to know whether the flyby had worked, whether the cameras had fired, whether 9 years of travel had produced anything at all. They sent a command, and then they waited. That is the distance to Pluto. Not a number on a page, a 4.5 hour silence. Now here is the belief that needs to be broken right now, cleanly, and without hesitation. Most people hear the phrase Pluto is in the solar system, and unconsciously translate that into something like, so it cannot be that far. This is one of the most deeply embedded misconceptions in popular understanding of space, and it is completely catastrophically wrong. The solar system sounds like a bounded place, a defined region, something with edges that a civilization might eventually reach and map. The name itself suggests a kind of order, a system, a structure that implies comprehensibility, and that implication is what leads people astray. Pluto sits in the Kuiper Belt, a vast ring of frozen debris that begins just beyond Neptune and extends billions of kilometers further into darkness. At its average position, Pluto is 39 times farther from the Sun than Earth is. Not 39% farther, 39 times farther. If the Earth-Sun distance were the length of a football field, Pluto would be sitting in the parking lot on the other side of the stadium in the dark, in a temperature that would kill an unprotected human in seconds. The solar system is not a cozy neighborhood, it is an empire, a sprawling, frozen, almost incomprehensibly vast empire, and humanity's fastest machine spent nearly a decade crossing just one corridor of it. And if that does not land with enough force, consider Voyager 1. It was launched in 1977. It has been flying continuously for 47 years without pause, without slowing, racing away from Earth at over 61,000 kilometers per hour. Scientists celebrated when it crossed into interstellar space in 2012, a genuine historic milestone, the first human-made object to leave the heliosphere. The enormous bubble of charged solar particles that surrounds our Sun and separates our solar system from the interstellar medium beyond. That was a real achievement, and it deserved every headline it received. But here is what those headlines often left out. Voyager 1 has still not left the full gravitational influence of the Sunday. The Oort cloud, the outermost shell of the solar system, a spherical halo of trillions of icy bodies held loosely in the Sun's gravitational grip, extends so far outward that it will take Voyager 1 approximately another 300 years just to reach its inner edge. And then somewhere between 20,000 and 100,000 additional years to exit it completely. 47 years of continuous flight at 61,000 kilometers per hour, and the spacecraft is still by any rigorous definition inside the solar system. It has not even reached the front gate. This is not a trivia problem. This is not a fun fact to share at dinner parties and then move on from. This is a survival problem, dressed in the language of science. If humanity cannot solve the distance equation, if civilization cannot find a way to travel faster, smarter, further, then every person who has ever lived, and every person who will ever live, remains confined to a single point in an ocean with no visible shore in any direction, one planet, one rock, one address in a cosmos that contains an estimated 2 trillion galaxies, each holding hundreds of billions of stars, and that planet, as stable and generous as it has been for 4 billion years, is not permanent. Asteroids have struck before and will strike again. Supervolcanoes have reshaped continents. Magnetic poles shift. The universe has ended potential civilizations before they developed language, and it will do so again indifferently without warning. The question of how hard it is to reach Pluto is therefore not academic. It is not a thought experiment for a quiet afternoon. It is the opening chapter of the most important long-term question our species has ever faced. After more than 60 years of space exploration, after the moon landings, the Mars rovers, the Hubble Space Telescope, the Voyager probes, the International Space Station, and the James Webb Space Telescope, humanity has still never sent a single living person beyond the moon. The moon sits 384,000 kilometers from Earth. Pluto is more than 15,000 times farther, and no human being has come within the same cosmic neighborhood of it. Why? After all this time, all this technology, all this ambition, why is the nearest dwarf planet still completely unreachable by human travelers? What is the actual obstacle, and what does it tell us about everything beyond? That is the question at the center of everything that follows. But before getting into why it is so hard, it is worth understanding exactly where Pluto actually sits, because the answer will make you see the solar system in a way that no textbook ever showed you. Every person who went through a science class has seen the same image. The solar system laid out in a neat horizontal diagram, the Sun positioned on the left, the planets lined up in order of distance, everything arranged in a way that looks almost manageable. Mercury sitting close to the Sun, then Venus, then Earth with its little moon, then Mars, then the asteroid belt, a modest scattering of rocks, and then Jupiter, Saturn, Uranus, Neptune, and somewhere at the far right edge of the poster, tiny Pluto included almost as an afterthought before the scientific community voted to reclassify it in 2006. The whole thing fits on a single page. It looks like a neighborhood. It looks like somewhere a civilization might explore over a few generations of determined effort. That image is a lie. Not a deliberate one, it is a lie of necessity. If any textbook tried to draw the solar system at true scale, most of the page would be completely blank. The planets would be invisible specks separated by expanses of white space so vast the diagram would communicate nothing useful. So scientists and educators made a collective unspoken decision: compress the distances, exaggerate the sizes, make it legible. The result is a picture that has over decades quietly but profoundly distorted humanity's intuitive sense of how big the solar system actually is. Here is what it actually looks like. Shrink the Sun down to the size of a basketball and place it in the middle of Times Square in New York City. At that scale, Earth becomes a sesame seed, a single sesame seed sitting approximately 26 meters away from the basketball. Not 26 kilometers, 26 meters. A person standing at the Sun could throw a baseball and come reasonably close to hitting the Earth. Mars becomes another sesame seed roughly 40 meters out. Jupiter, the largest planet in the solar system, large enough to swallow 1,300 Earths, shrinks down to a marble. A marble sitting approximately 135 meters from the basketball, roughly the distance from one end of a city block to the other. And Pluto becomes a grain of sand. A single grain of sand so small it is invisible to the naked eye, sitting in Central Park 1 full kilometer away from that basketball in Times Square. 1 kilometer of Manhattan between the Sun and Pluto. Walk out of Times Square through the theatre district, past the edge of the park and into the trees, and somewhere in there, too small to see, is the destination that took 9 years and 5 months to reach. This is not poetic exaggeration. This is the actual ratio, and the space between that basketball and that grain of sand almost entirely empty. No air, no warmth, no sound. Just radiation, darkness, and the occasional stray particle. Saying Pluto is close to Earth because they share. The solar system is like saying Los Angeles is close to Boston because they are both in the United States. Technically accurate. Completely useless as a practical statement about the experience of crossing the distance. Now even that scale model does not tell the full story, because Pluto is not the edge, not even close. The solar system has 3 major structural layers beyond the inner planets. First, the asteroid belt between Mars and Jupiter, a region that science fiction has traditionally depicted as a dangerous gauntlet of crashing rocks, but which is in reality mostly empty space, with debris distributed so sparsely that the spacecraft ever launched has passed through it without incident. Then comes the Kuiper Belt, beginning just beyond Neptune at roughly 30 astronomical units from the Sun and extending out to about 50 astronomical units. This is where Pluto lives. This is where New Horizons travelled for 9 years to reach. And in that basketball in Times Square model, the entire Kuiper Belt fits within a few additional meters past Central Park. But the third layer is where the solar system stops being a place and starts being a concept. The Oort cloud is the outermost boundary of the Sun's gravitational domain. Unlike the flat rings of the asteroid belt and the Kuiper Belt, the Oort cloud is a spherical shell, a 3-dimensional halo that completely encases the entire solar system in every direction, above, below, and to all sides. It is composed of trillions of icy objects, leftover fragments from the formation of the planets held in the Sun's gravitational grip at distances almost too large to process. The Oort cloud extends from roughly 2,000 astronomical units all the way out to 100,000 astronomical units from the Sunday. In the basketball in Times Square scale, the outer edge of the Oort cloud would sit somewhere in Philadelphia. Light travels at 300,000 kilometers per second. At that speed, it crosses the distance from Earth to the Moon in just over 1 second. It reaches Mars in between 3 and 22 minutes, depending on orbital positions. It gets from Earth to the Sun in 8 minutes. But light moving at that same incomprehensible speed would need more than 1.5 years to travel from the Sun to the outer edge of the Oort cloud. To cross the entire Oort cloud entering one side and exiting the other would take light 3 full years. 3 years at the speed of light just to pass through the outermost layer of the solar system. Voyager 1, flying for 47 years at 61,000 kilometers per hour, has not yet reached it. This is the real map, not a poster, not a diagram. An empire so large that the fastest thing in the universe needs years to cross its borders, and humanity's best machine needs centuries just to approach them. How long do you think New Horizons spent in the vicinity of Pluto after that 9-year journey? Did it slow down and orbit? Did it take its time, settle into the neighbourhood, collect data over days or weeks before moving on? One day, maybe, a week. The answer is coming, and it changes everything about how the physics of this journey actually feels. Knowing the map is one thing, but the real challenge is not the distance. It is something that no rocket on Earth can overcome by simply flying in a straight line. There is a problem buried inside the dream of going fast. A mathematical trap that engineers have known about for over a century and that no amount of ambition or funding has yet managed to escape. It does not care about budgets. It does not respond to political will. It is simply the way the universe is built, and it has been quietly strangling humanity's reach into deep space since the first rocket ever left the ground. The trap works like this. To go faster, a spacecraft needs more fuel, More fuel makes the spacecraft heavier. A heavier spacecraft requires even more fuel just to accelerate to the same speed. But that additional fuel also adds weight, which demands still more fuel to move, which adds more weight, which demands more fuel again. The cycle feeds on itself without mercy, each step requiring a larger commitment than the last, the numbers spiraling outward in a way that feels almost personal in its cruelty. This relationship was formalized in 1897 by the Russian mathematician Konstantin Tsiolkovsky, and the equation bearing his name has been the governing reality of spaceflight ever since. No engineering breakthrough has repealed it. No new material or clever design has found a workaround. The rocket equation is not a temporary obstacle. It is a fundamental constraint written into the physics of how mass and momentum interact. The practical consequence is this: to double a spacecraft's speed, using chemical propulsion, the amount of fuel required does not double. It increases by a factor of many times over, sometimes 10, sometimes far more depending on the specific velocities involved. The relationship is exponential, not linear, and that single fact has defined the ceiling of what humanity can reach. The Saturn V rocket stands as the most dramatic illustration of this constraint ever built. It remains the most powerful launch vehicle in history, the machine that carried the Apollo astronauts to the moon, and has never been surpassed in raw thrust. When it sat on the launch pad, fully loaded and ready to fly, it weighed approximately 2,900,000 kilograms. Of that total mass, 96% was fuel, 96%. The actual spacecraft, the capsule, the lunar module, the instrumentation, the human beings inside, represented just 4% of everything sitting on that pad. The Saturn V was not really a spacecraft with fuel attached. It was a fuel tank with a spacecraft riding on top, burning through nearly 3,000 kilograms of propellant every single second during its initial ascent. And the moon is only 384,000 kilometers away. Pluto is 15,000 times farther. New Horizons was launched in January of 2006 and immediately became the fastest spacecraft humanity had ever sent into the cosmos. At the moment of launch, after the Atlas V rocket had burned its fuel and the additional solid fuel boosters had fired and released, New Horizons was traveling at 58,536 kilometers per hour. That is the number that represents the practical ceiling of chemical propulsion technology. Not a speed chosen for convenience or budget, but a speed representing the maximum that the physics of burning fuel against mass could produce with the hardware available. Engineers did not hold back. That was the limit. And then they needed more speed, because even at 58,536 kilometers per hour, the journey to Pluto would take an unacceptably long time without additional acceleration. But there was no more fuel. The rocket had burned everything it had. So the mission planners turned to something else entirely, a technique that sounds almost like cheating because in a sense it is. Gravity assist. The principle is elegant and slightly absurd at the same time. A spacecraft approaching a massive planet, Jupiter in this case, enters the planet's gravitational field and gets pulled toward it, accelerating as it falls. But instead of hitting the planet or entering orbit, the spacecraft is angled to swing around it, using the planet's own orbital momentum to slingshot outward at a higher speed than it came in with. No fuel burned, no chemical reaction. Just the spacecraft, borrowing kinetic energy from a planet that is itself moving through space, exploiting the gravitational geometry of the solar system like a cosmic billiard shot calculated years in advance. New Horizons swung past Jupiter in February of 2007, 13 months after launch. The flyby added 14,000 kilometers per hour to its velocity, for free. No propellant consumed, no engine fired. Jupiter simply handed over a portion of its own momentum too massive to notice the theft. The encounter also cut years off the mission timeline. Without that gravity assist, New Horizons would have reached Pluto significantly later, or might not have reached it at all within a feasible mission window. The gravity assist is one of the most elegant ideas in the history of space exploration. It is also, if you look at it from a certain angle, a confession. It is an admission that chemical rockets cannot do the job alone, that humanity's best engines burning the most energetic fuels available, pushing against the iron wall of the Tsiolkovsky equation, are simply not enough to cross the solar system in any reasonable time frame without borrowing momentum from planets along the way, like a car with no gas rolling downhill to gather speed and hoping the hill is long enough. The gravity assist bought time, it bought speed, it made New Horizons possible, but it is not a solution to the fundamental problem. It is a workaround, a brilliant workaround, but a workaround nonetheless. So even with the fastest launch in history, even with a perfectly calculated slingshot around the largest planet in the solar system, even with engineers optimizing every variable they could touch, it still took 9 years and 5 months. So even flying as fast as physically possible, it still cost nearly a decade. But why did New Horizons not stop at Pluto? The answer is one of the most painful truths in all of physics. On the 14th of July 2015, New Horizons reached its closest approach to Pluto. After 9 years and 5 months of travel, after billions of kilometers of empty space, after surviving the cold and the radiation and the extraordinary loneliness of deep space, the spacecraft arrived. And it did not slow down for even 1 second. New Horizons flew past Pluto at 49,600 kilometers per hour. At that speed, the entire encounter from the moment Pluto filled the cameras to the moment it receded back into darkness lasted precisely 72 hours. That was the window. 72 hours at closest approach to photograph a world that no human eye had ever seen clearly. The cameras fired continuously. The instruments measured everything they could measure. The onboard systems worked at maximum capacity, collecting data on the atmosphere, the surface composition, the temperature, the moons, the magnetic environment. 72 hours of furious, desperate science, and then Pluto was gone, falling behind at 49,600 kilometers per hour, and New Horizons continued onward into the Kuiper Belt, still moving, still accelerating, slightly due to residual trajectory effects, never to return. It did not stop, because it could not stop. And the reason it could not stop is the same reason a crewed mission to Pluto remains with current technology essentially a fantasy. In space there is no friction, no air resistance, no surface to push against, nothing to slow a moving object down. A spacecraft travelling at 49,600 kilometers per hour will continue travelling at 49,600 kilometers per hour indefinitely, unless something actively pushes against it. The only way to decelerate is to fire an engine in the direction of travel to push backward against the velocity. But firing an engine requires fuel, and the amount of fuel required to slow down is roughly equivalent to the amount required to speed up in the first place. New Horizons used an entire Atlas V rocket plus additional boosters just to reach its departure velocity. To stop at Pluto, it would have needed an equivalent amount of thrust applied in reverse. It carried none of that. It was never designed to. Because carrying that much additional fuel from Earth would have made the spacecraft so heavy that it could never have been launched to begin with. This is the Tsiolkovsky equation, again tightening its grip from the other direction. Now consider what a crewed mission to Pluto would actually require. Not a flyby, a real mission with human beings who need to arrive, conduct meaningful research and then come home. The fuel math becomes almost absurdist. First, enough propellant to accelerate a significantly heavier crewed vessel. Heavier because humans require life support systems, food, water, radiation shielding, psychological accommodations, medical equipment to the velocities needed for the journey. Then, additional fuel to decelerate that vessel into Pluto orbit upon arrival, fighting against the same momentum that the departure burn created. Then fuel to exit Pluto's gravitational influence when the mission concludes. Then fuel to accelerate back toward Earth. Then fuel to decelerate into Earth orbit for safe return. Each of these burns requires its own propellant budget, and each additional kilogram of fuel added to the spacecraft demands still more fuel to carry it. The recursive nightmare of the rocket equation, playing out across 5 separate major burns over a round trip measured not in months, but in decades. NASA's engineering analyses of crewed deep space missions have consistently arrived at the same uncomfortable conclusion. A crewed mission to Pluto using chemical propulsion would require a spacecraft with a fuel mass comparable to the International Space Station. The International Space Station took over a decade to assemble, required more than 40 separate launches, and has a mass of approximately 420,000 kilograms. That is what would be needed not for the science payload, not for the crew quarters, not for the return vehicle, just for the fuel, just to move. And then there is the human body itself, which turns out to be extraordinarily poorly designed for this particular journey. 9 years in space is not a long time in cosmic terms. It is an eternity in biological ones. Beyond Earth's magnetosphere, the protection that has shielded life on this planet for billions of years vanishes. Cosmic rays, high-energy particles accelerated by distant supernovae, and galactic processes pass through spacecraft walls and human tissue with relative ease. They break DNA strands, they damage cell membranes. They accumulate in ways that no amount of shielding yet devised can fully prevent. Astronauts aboard the International Space Station, still within partial protection of Earth's magnetic field, show measurable changes in brain structure and cognitive function after just 6 months. 9 years in open space is not a scaled-up version of 6 months in low Earth orbit. It is a different category of exposure entirely. Meanwhile, without gravity, the human body quietly dismantles itself. Muscles atrophy because they have nothing to work against. Bones lose density at rates that even with aggressive exercise regimens cannot be fully countered. The cardiovascular system, no longer fighting against gravity to pump blood upward, restructures itself in ways that cause problems when gravity returns. Astronauts returning from 6-month missions on the space station require months of rehabilitation to walk normally. A 9-year mission in microgravity presents physiological challenges that medicine has not yet solved. And then there is the mind. Isolation studies not in space, but in Antarctic research. Stations in submarines and simulated Mars habitats consistently show that psychological deterioration begins within months. Conflict escalates. Motivation collapses. Depression, paranoia, and interpersonal breakdown emerge in people who were specifically selected and trained for exactly these conditions. 9 years in a closed metal container, with a communication delay of 4.5 hours to Earth, with no possibility of rescue or resupply with darkness in every window that is not a mission profile. That is something closer to a sentence. If you could choose a one-way flight to Pluto with no return ticket or staying on Earth, what would you choose? It sounds like an easy answer. But when that question has been posed to actual astronauts and cosmonauts, people who have already spent months in space and understand viscerally what isolation and confinement feel like, a striking number of them say they would go. Not because dying on Pluto is appealing, but because being the first to stand on another world at the edge of the solar system, even for a moment, even without coming back for certain kinds of people, that is not a sacrifice. That is the whole point. But the cost of getting there is only half the story. What New Horizons actually found when it arrived, that is the part nobody saw coming. Before the 14th of July, 2015, Pluto was a blur. Not metaphorically, literally. Every image ever captured of Pluto before that date, including those taken by the Hubble Space Telescope, the most powerful optical instrument humanity had placed in orbit, showed a smeared, pixelated disk of indistinct colour. Its surface, features unresolvable. Its geography, a complete mystery. For 85 years after its discovery in 1930, Pluto existed in human knowledge as a number, a distance, a mass estimate, a dot of reflected light that told scientists almost nothing about what was actually there. Entire generations of astronomers studied it without ever seeing it. They measured its orbit, calculated its density, detected its moons, but the world itself remained hidden too far away and too small for any telescope on or near Earth to bring into focus. Then New Horizons arrived, and in the span of 72 hours, 85 years of blindness ended. The images that came back were not what anyone expected, not even close. Scientists had prepared themselves for a dead world, a frozen, cratered, geologically inert rock that had been sitting unchanged in the outer darkness for billions of years, battered by micrometeorites stripped of any atmosphere worth, measuring its surface as featureless and ancient as the bottom of an ad. Empty bowl. That was the reasonable prediction. That was what the physics seemed to suggest. A world that's small, that far from the sun, receiving that little energy, should have exhausted any internal heat source eons ago. Nothing should be happening on Pluto. Nothing should have happened there for a very long time. What New Horizons found instead was a world that was actively alive. Mountain ranges of water ice rose to heights of 3,500 meters, comparable to the Rocky Mountains, their peaks sharp and young-looking, suggesting they had not been eroded by billions of years of micrometeorite. impacts the way truly ancient terrain would be. Young mountains mean recent geological activity. Recent geological activity on a world with no obvious internal heat source means something in the physics of Pluto is not yet fully understood. Scientists are still debating the mechanism. The mountains should not be there, but there they are. Then there was the heart. Officially named the Tombaugh Regio, in honour of Clyde Tombaugh, the astronomer who discovered Pluto in 1930, the region is a vast plain of frozen nitrogen, shaped unmistakably like a heart, a smooth, pale, almost luminous expanse, roughly the size of Texas sitting against Pluto's darker, more rugged terrain. The western lobe of this heart, called Sputnik Planitia, is one of the most geologically complex features ever found in the outer solar system. It shows evidence of convection, slow churning movement of the nitrogen ice itself, driven by subtle heat from below, creating a constantly renewing surface. Parts of it appear to be geologically recent. In planetary terms, recent can mean within the last few 100 million years, but on a world expected to have been dead for billions, recent is extraordinary. Above all of this, thin, delicate, and completely unexpected was an atmosphere. Not a thick atmosphere, nothing like Earth's, but a haze layer of organic compounds extending hundreds of kilometers above the surface, tinted blue by the scattering of sunlight through particles of complex chemistry called tholins. Blue. Pluto has a blue sky. Not a sky anyone could breathe in. Not a sky that could protect a living thing from radiation. But a sky nonetheless. A thin veil of atmosphere that changes with Pluto's seasons as it swings through its 248-year orbit around the Sun, freezing and sublimating and reorganizing in ways that scientists are still working to fully characterize. Pluto had been stripped of its planetary status in 2006, reclassified as a dwarf planet by the International Astronomical Union, in a vote that generated more public controversy than most decisions made by any scientific body. In recent memory, the demotion happened the same year New Horizons launched a timing that carried its own peculiar irony. By the time the spacecraft arrived, the world had already decided Pluto was not important enough to be a planet. And then the images came back and the world changed its mind about what Pluto was allowed to be. Not in the official classification that stands, but in imagination, in wonder, in the way people felt about a small frozen world at the edge of the solar system when they finally saw its face for the first time. Pluto earned something that no reclassification could take away. Now consider what it costs to receive that knowledge. The data collected during the 72-hour flyby was not transmitted instantly. It could not be. The signal, carrying every photograph, every atmospheric measurement, every spectrographic reading, every temperature map, that signal travelled at the speed of light across 5.9 billion kilometres of space, arriving at Earth 4.5 hours after it was sent. But the sheer volume of data New Horizons collected during the encounter was so large that the spacecraft's transmitter, limited by power and antenna size, could only send it back at a rate comparable to an early dial-up internet connection, slower in some cases. Transmitting the complete dataset from the Pluto flyby took 16 months. 16 months of continuous downlink. The dishes of NASA's Deep Space Network pointed at a tiny spacecraft, billions of kilometers away, listening patiently to a trickle of information, arriving at the speed of light, but dripping through. A strav. 16 months to receive the data from a single 72-hour encounter. New Horizons did not stop after Pluto. It could not stop, that much has already been established. It continued deeper into the Kuiper Belt, still operational, still collecting data. Its instruments turned outward toward new targets. On the 1st of January 2019, it flew past Arakoth, a small contact binary Kuiper Belt object located approximately 6.6 billion kilometers from the Sun, and the most distant object ever explored by a spacecraft. Up to that point, Arakoth turned out to be a gently joined pair of lobes, shaped like a flattened snowman, its surface reddish and ancient, a pristine remnant from the formation of the solar system itself. Again, the encounter revealed something unexpected. Again, the universe declined to be boring. At the time of this writing, New Horizons is still out there, still moving, still alive. Its plutonium power source, a radioisotope thermoelectric generator that converts the heat of radioactive decay into electricity, produces roughly the same power output as 2 standard 100-watt light bulbs. That is the energy budget. 2 light bulbs. And on that power, an object roughly the size of a grand piano is navigating the outer Kuiper belt. Billions of kilometers from the nearest human being, transmitting data back to Earth across a silence so vast it takes hours to cross, even at the speed of light. There is something almost unbearably poignant about that image. A piano-sized machine alone in the dark, powered by less electricity than it takes to light a small room carrying instruments that are slowly losing power year by year as the plutonium decays, still doing science, still sending home what it finds. It will eventually go quiet sometime in the late 2030s when the power finally drops below the threshold needed to operate any instruments at all. And then it will continue outward in silence, an artifact of a civilization that built it and launched it and listened to it for decades, drifting into the outer solar system for millions of years with no one left to hear it. Pluto was stripped of its planetary title, and then it turned out to be one of the most astonishing worlds that any instrument of human curiosity has ever reached. A world with mountains that should not exist, a heart made of frozen nitrogen, a blue haze of alien chemistry hanging over everything, and geological processes still quietly reshaping its surface in the dark. That was only the first stop. If reaching Pluto was this hard, then the nearest star, Proxima Centauri, is not just a little harder. It belongs to an entirely different dimension of the problem. 4.24 light-years. It sounds almost reasonable. A small number. A number that fits comfortably on a page that can be spoken in a single breath that carries none of the visual weight of what it actually represents. 4.24. People hear that, and somewhere in the back of the mind, without conscious awareness, a quiet reassurance settles in. That is not so bad. That is manageable. Proxima Centauri is the closest star to our Sun, and 4.24 light-years does not sound like much of a distance at all. Here is what 4.24 light-years actually is. 40,208 billion kilometers. Written out in full, 40,208 billion kilometers. If that number still fails to produce the correct emotional response, try it this way. New Horizons, the fastest spacecraft humanity has ever launched. The machine that took 9 years and 5 months to reach Pluto at 58,000 kilometers per hour would need 73,000 years to reach Proxima. Centauri at its current speed. Not 73 years, not 730 years, 73,000 years. The last ice age ended roughly 11,000 years ago. Agriculture was invented around 10,000 years ago. The pyramids at Giza were built approximately 4,500 years ago. Every monument, every empire, every language, every war, every discovery, every human life ever lived. The entire arc of recorded civilization, from the first clay tablets in Mesopotamia to this moment, spans roughly 5,000 years. 5,000 years is less than 1/14 of the time it would take New Horizons to reach the nearest star. Let that proportion sit for a moment. Not the number itself, but the ratio. Everything humanity has ever done compressed into a single unit of time, and that unit does not even get the spacecraft 1/14 of the way there. Now here is the question worth pausing on. If the entire journey from Earth to Pluto, 5.9 billion kilometers, 9 years and 5 months, at maximum chemical velocity, were shrunk down to 1 centimeter. 1 centimeter. The length of a fingernail. Then at that same scale, how far away would Proxima Centauri be? The answer is approximately 710 meters, more than 7 city blocks. On a scale where the entire Earth to Pluto distance fits under a fingernail, the nearest star is 7 blocks away. Pluto, which already seemed impossibly remote, which already required the fastest machine ever built, and nearly a decade of flight, is not even a rounding error on the journey to the closest point of light in the night sky. This is the number that changes everything, not the abstract distance in kilometers which the human brain cannot genuinely process at that scale, but the ratio. Pluto to Proxima Centauri is not 1 step to 2 steps. It is 1 grain of sand to a stretch of beach. And yet Proxima Centauri is universally described as the nearest star, the closest one, the most accessible point of light beyond our own Sunday. Every popular science article, every documentary, every conversation about interstellar travel begins with Proxima Centauri, precisely because it is the shortest distance to the next star system. This is the bottom of the staircase. This is the easiest possible first step beyond the solar system. That word nearest is doing an enormous amount of dishonest work. In everyday language, nearest implies accessible. It implies that the effort required is at least proportional to something a civilization might feasibly undertake. When someone says the nearest gas station is 3 miles away, nearest means something useful. When astronomers say Proxima Centauri is the nearest star, they are using the same word to describe a distance so vast it dissolves the meaning of the concept entirely. Calling Proxima Centauri close because it is the nearest star is like standing at the base of Mount Everest, looking up at the summit and saying it is not that high compared to the radius of the Earth. Technically accurate, the summit of Everest is 8.8 kilometers above sea level. The radius of the Earth is 6,371 kilometers. By that comparison, Everest barely registers, and yet no one standing at its base. Looking up through the thinning air at the ice and the wind and the altitude that has killed hundreds of experienced climbers would call it a modest hill. Nearest in cosmic terms is not a description of proximity. It is a description of which impossibility is the least impossible. 73,000 years at the speed of new horizons. 5,000 years of human civilization. 1 centimetre versus 710 metres. These are not numbers designed to discourage. They are numbers designed to establish an honest baseline, because the instinct when confronted with a problem this large is to immediately reach for hope, to say, well, we will build faster ships, we will find better propulsion, the technology will improve. And that instinct is not wrong, it is in fact the only productive response, but it has to be grounded in a clear-eyed understanding of exactly how large the gap is between where humanity stands right now and what reaching another star system would actually require. Without that understanding, the optimism is not courage. It is just comfortable ignorance wearing the costume of ambition. The nearest star is 4.24 light-years away. That is the problem. Everything else that follows is humanity's attempt to figure out what to do about it, but the distance is only the surface of the problem. The real challenge lies in how to go fast enough, and why even fast becomes a trap. 299,792 kilometers per second. That is the speed of light, not an approximation, not a round number chosen for convenience. That is the precise measured velocity of a photon, moving through a vacuum confirmed by experiment after experiment, across more than a century of physics. It is also, according to Albert Einstein's special theory of relativity, the absolute speed limit of the universe. Not a record waiting to be broken by better engineering, not a barrier that will yield to sufficiently advanced technology. A hard wall embedded in the structure of space-time itself, the point at which the equations break down entirely and the physics simply refuses to cooperate further. Nothing with mass can reach it. Objects with mass can approach it. They can get very close, asymptotically close, but the energy required to accelerate a massive object increases without bound as its velocity approaches the speed of light. To actually reach it would require infinite energy. The universe does not have infinite energy to spare. So the question is not how to travel at the speed of light. The question is how close humanity might realistically get, and what happens to space and time as that limit is approached. Start with something sobering. If a spacecraft could somehow reach 10% of the speed of light, that is 29,979 kilometers per second, roughly 2,000 times faster than New Horizons, a velocity so extreme it dwarfs everything humanity has ever achieved, the journey to Proxima Centauri would still take 42 years. 42 years at 10% of the speed of light. An astronaut who left Earth at 30 years old would arrive at 62 if they survived the journey at all. Their children would be middle-aged. Their parents would likely be dead. A round trip, if they turned around immediately upon arrival, would take 84 years. They would return to an Earth where everyone they had known as a young adult was gone. And 10% of the speed of light is so far beyond anything currently possible that it might as well be magic. New Horizons travels at roughly 0.005% of the speed of light. The gap between what humanity has built and what 10% of light speed would require is not a gap in degree, it is a gap in kind. Push the scenario further. Imagine a spacecraft travelling at 90% of the speed of light, Here is where physics stops being intuitive and starts being genuinely strange. From the perspective of observers on Earth, the journey to Proxima Centauri at 90% light speed would take approximately 4.7 years the distance, divided by the velocity straightforward enough. But the astronauts on board would not experience 4.7 years. They would experience something significantly shorter. This is time dilation, one of the confirmed experimentally verified consequences of Einstein's special theory of relativity. As an object moves faster through space-time, for that object passes more slowly relative to stationary observers. Not as a biological trick, not as a perceptual illusion, not as a consequence of stress or isolation, as a literal, measurable physical fact about the nature of time itself. At 90% of the speed of light, the time dilation factor means that while 4.7 years pass on Earth, the astronauts on the spacecraft would experience just over 2 years of elapsed time. They would arrive at Proxima Centauri having aged roughly 2 years. Earth would have aged 4.7. The gap between those two numbers is real. The astronauts would, in a precise and literal sense, be travelling into the future of the people they left behind. This is not science fiction. Atomic clocks placed on commercial aircraft moving at a few hundred kilometers per hour, an almost negligible fraction of light speed returned to the ground, having registered slightly less time than identical clocks left on the surface. The difference is tiny, a matter of nanoseconds, but it is real and measurable, and exactly consistent with what relativity predicts. GPS satellites require constant correction for relativistic time dilation to maintain their accuracy. The effect is not hypothetical. It operates right now, every day, in technology that millions of people use without thinking about it. The twin paradox pushes this further into territory that feels philosophically vertiginous. Send one twin on a relativistic spacecraft journey while the other remains on Earth. When the travelling twin returns, they are younger, genuinely biologically measurably younger than the twin who stayed home. Not by much at currently achievable speeds, but at a significant fraction of light speed the difference becomes dramatic. A journey that feels like 2 years to the astronaut might correspond to a decade or more on Earth. The traveller returns younger than their own children. Theoretically, if a spacecraft could reach 99.999% of the speed of light, time dilation becomes extreme enough that the astronauts could traverse interstellar distances experiencing only months or years of personal time, even as centuries pass on Earth. The universe would, in a sense, become more accessible, but only to the traveller. They would return to a world that had moved on without them by generations. And then there is the energy problem. As velocity increases toward the speed of light, the energy required increases without limit. At 90% of light speed, the kinetic energy of even a modest spacecraft would be equivalent to thousands of nuclear warheads. At 99%, the numbers become absurd. The closer to the speed of light, the steeper the energy curve rising toward infinity as the limit approaches, demanding more than the universe is willing to provide. In theory, if you travel fast enough, you will return home younger than your own children. That is, practically speaking, the most expensive anti-aging strategy ever conceived. So if chemical rockets are impossible and the speed of light is an unreachable dream, does humanity have any plan that is more realistic? The answer exists, and it is stranger than anything science fiction has managed to imagine. In 2016, billionaire investor Yuri Milner stood on a stage in New York and announced something that sounded on first hearing like the premise of a science fiction novel written by someone who had given up on plausibility. He was joined in spirit and in endorsement by Stephen Hawking at that point, the most recognizable physicist alive. Together they announced Breakthrough Starshot, a project to send a spacecraft to Proxima Centauri within a human lifetime. Not a crude spacecraft, not a vessel the size of a school bus or a station or anything resembling what the word spacecraft typically conjures. What Milner and Hawking proposed was a fleet of spacecraft the size of postage stamps. Literally, each individual craft, called a starship, would be a wafer of silicon roughly 4 centimeters across, carrying miniaturized cameras, communication systems and navigation instruments attached to a sail of reflective material, only a few hundred, atoms thick. Hundreds or thousands of these would be launched into orbit, and then from a ground-based installation on Earth, an array of high-powered lasers would fire simultaneously at the sails. The concentrated light pressure from those lasers would accelerate the tiny craft to 20% of the speed of light in a matter of minutes. At that velocity, the journey to Proxima Centauri would take approximately 20 years. The first images of another star system could arrive on Earth within the lifetimes of people alive today. The elegance of the concept is real. By making the spacecraft almost massless, the energy required to accelerate it drops from the astronomical figures associated with conventional propulsion to something at least theoretically achievable. Light pressure, the force exerted by photons, striking a surface, is real and measurable. Solar sails have already been demonstrated in space by the Japanese Icaros mission and the Planetary Society's light sail projects. The physics of laser-driven propulsion is not in dispute. Breakthrough Starshot is not pseudoscience. It is a genuine engineering challenge being taken seriously by serious people. But the challenges are severe enough to deserve their own moment of honesty. The laser array required to accelerate even a gram-scale spacecraft to 20% of the speed of light would need to deliver approximately 100 gigawatts of power during the acceleration phase. 100 gigawatts is roughly equivalent to the entire electrical generating capacity of the United States at any given moment. Every power plant, every solar farm, every wind turbine, every nuclear reactor, all of it pointed at a postage. Stamp in orbit for a few minutes. Building and powering such an array represents an engineering undertaking that dwarfs anything humanity has attempted. The cost estimates for the full system run into the tens of billions of dollars at minimum, and that assumes solutions to engineering problems that have not yet been solved. Then there is the interstellar medium. Space between stars is not empty. It contains sparse clouds of gas and microscopic dust particles, densities so low they are essentially vacuum by any earthly standard. But at 20% of the speed of light, a single grain of sand becomes a catastrophic impact. Event. A dust particle striking the star chip at that velocity would release energy comparable to a small explosive charge. The sail-only atoms thick would be shredded. The silicon wafer behind it would be obliterated. Engineers are working on materials that might survive the onslaught: layered structures, self-healing coatings, angled geometries designed to deflect rather than absorb impacts. But no solution has yet been demonstrated at the required scale. Breakthrough Starshot is the most credible near-term proposal for reaching another star, and it is still decades away from being buildable, if it is buildable at all. Other proposals exist, and some of them have been on the table far longer. Nuclear pulse propulsion. The concept of detonating a series of nuclear bombs directly behind a spacecraft and riding the successive shockwaves was seriously studied in the United States under Project Orion from the late 1950s through the early 1960s. The physicist Freeman Dyson, one of the most respected theoretical minds of the 20th century, was among its advocates. The physics worked. Models were built and tested with conventional explosives. Trajectory calculations showed that a nuclear pulse vessel could potentially reach velocities of several % of the speed of light fast enough to make interstellar travel conceivable within extended human timescales. The project was cancelled not because the engineering failed, but because the Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space. A technology that was physically viable was stopped by international law. It remains stopped. The Outer Space Treaty and subsequent arms control agreements have kept it that way. Antimatter propulsion operates on a different level entirely. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass directly into energy, according to Einstein's equation relating energy mass and the speed of light squared. No chemical reaction, no nuclear fission, no fusion process approaches this efficiency. 1 gram of antimatter combined with 1 gram of ordinary matter releases energy roughly equivalent to nearly 3 times the atomic bomb dropped on Hiroshima in 1945. The energy density is essentially the highest the laws of physics permit. A spacecraft powered by antimatter annihilation in theory could achieve velocities that make interstellar travel within human lifespans genuinely plausible. In theory. The production problem is paralyzing. Antimatter does not exist in useful quantities anywhere in the accessible universe. It must be manufactured particle by particle using particle accelerators. The entire global infrastructure of high-energy physics research produces only a few nanograms of antihydrogen per year, and at enormous energetic cost. NASA has estimated that producing a single gram of antimatter using current technology would require approximately $62.5 trillion, not $62.5 billion, $62.5 trillion, the entire gross domestic product of the United States for roughly 2.5 years spent to produce an amount of fuel that fits on the head of a pin. Antimatter propulsion is not an engineering challenge. It is a civilizational challenge of a different order. And then there is the Alcubierre warp drive, the idea that makes physicists pause before answering because it occupies the strange borderland between legitimate mathematics and complete physical mystery. In 1994, Mexican physicist Miguel Alcubierre published a paper demonstrating that general relativity, Einstein's theory of gravity and spacetime, permits a solution in which a bubble of flat spacetime moves through the surrounding spacetime at arbitrary speed. A spacecraft inside the bubble would not be moving through space. The space itself would be moving around it, contracting ahead and expanding behind. Since the spacecraft is locally stationary within its bubble, it violates no speed limit. Relativity is not broken. The math is valid. What is required to generate this bubble is exotic matter, with negative mass, a substance that has never been observed, whose existence is not confirmed, and whose physical properties would violate assumptions so fundamental to known physics that most researchers consider it essentially fictional. There are ongoing theoretical discussions about whether quantum field effects near the bubble walls might provide some analogue of negative energy density, but these remain highly speculative. The Alcubierre drive is mathematically consistent. Whether it corresponds to anything that can exist in reality is an entirely open question. Of all these technologies, laser sails, nuclear pulse engines, antimatter drives, warp bubbles, which has the best chance of becoming real within the next 100 years. Many physicists, when pressed, give an answer that surprises people. Not the most dramatic option, not the most exotic, the one that requires the fewest violations of currently understood physics. The answer and the reasoning behind it is worth sitting with. But even solving the speed problem leaves one challenge that nobody has solved yet: how to keep human beings alive for the journey. Assume, for the sake of argument, that the engineering problems get solved. Assume that sometime in the next century, humanity develops a propulsion system capable of driving a crewed spacecraft to Proxima Centauri in 20 years. Assume the funding materializes, the international cooperation happens, the spacecraft gets built and launched. The crew is aboard. The destination is set. The human body will immediately begin trying to destroy itself. Outside Earth's magnetosphere, the invisible magnetic shield generated by the planet's molten iron core, which deflects the majority of high-energy cosmic radiation. The radiation environment of deep space is unrelenting. Astronauts aboard the International Space Station, which orbits at an altitude of approximately 400 kilometers and still receives partial protection from Earth's magnetic field, absorb radiation at a rate roughly 100 times higher than a person living on the surface. 6 months on, the station delivers a radiation dose that, while carefully managed and monitored, already raises long-term cancer risk in ways that NASA tracks meticulously across the careers of its astronauts. A crewed interstellar mission operating entirely outside any planetary magnetic protection for 20 years would expose the crew to radiation levels orders of magnitude beyond what any human being has ever survived. Cosmic rays, high-energy atomic nuclei, accelerated to near light speed by distant supernovae, and other violent astrophysical processes pass through conventional shielding with relative ease. They do not stop at metal walls. They interact with shielding material in ways that can actually generate secondary radiation, creating cascades of particles that in some configurations make things worse rather than better. The DNA damage accumulated over 20 years of unshielded deep space travel would be, by current medical understanding, incompatible with survival. The crew would not arrive. They would die along the way from cancers, from organ failure, from the slow cellular destruction of a radiation dose that has no precedent in human medicine. And radiation is only the first problem. The human musculoskeletal system evolved over millions of years in the presence of Earth's gravity. One standard gravity, constant and unavoidable, shaping every bone density, every muscle mass, every cardiovascular adaptation the body makes. Remove that gravity and the body begins immediately and systematically to dismantle the infrastructure it no longer needs. Muscles atrophy because there is nothing to push against. Bones lose density because the mechanical stresses that signal bone maintenance are gone. The cardiovascular system restructures because the heart no longer needs to work against gravity to push blood upward. Astronauts returning from 6-month missions aboard the International Space Station 6 months. A small fraction of a 20-year interstellar journey typically require several months of intensive rehabilitation before they can walk normally. Some experience lasting changes in vision caused by fluid shifts within the skull. Some show measurable cognitive changes. 20 years of microgravity would not be a scaled-up version of 6 months. The body would reach states of deterioration that rehabilitation might not be able to reverse. Arriving at Proxima Centauri after 20 years in zero gravity, the crew might not be able to stand up. Then there is the mind. NASA has conducted and funded extensive research into the psychological effects of isolation and confinement, including analog studies in Antarctic research stations and nuclear submarines in simulated Mars habitats. The findings are consistent across environments and populations. Within months of isolation in a small group with no external contact, conflict escalates, social hierarchies destabilize, depression, anxiety, paranoia, and interpersonal breakdown emerge even among individuals specifically selected and trained for exactly these conditions. The crews that do best are still profoundly affected. 20 years in a closed vessel with no possibility of outside intervention with the nearest human civilization, 4 light-years away. That is not a psychological challenge with existing solutions. That is a psychological challenge that has never been faced, and for which there is no precedent anywhere in human history or clinical literature. And there is no calling for help. A distress signal sent from the vicinity of Proxima Centauri would take 4.24 years to reach Earth. The response would take another 4.24 years to return. If a crew member suffers a medical emergency, if a critical system fails, if a decision needs to be made that requires expertise back home, the round-trip communication delay is 8.5 years. The crew is in every practical sense completely alone. Researchers are working on solutions. NASA has funded studies into suspended animation, the idea of placing crew members in a state of significantly reduced metabolism during the long transit phase, lowering body temperature, slowing breathing and heart rate, reducing the subjective experience of time and simultaneously reducing food, consumption, radiation, damage accumulation, and psychological deterioration. Hibernation essentially in controlled medical form. The technology exists in primitive versions. Therapeutic hypothermia is used in certain cardiac procedures, but inducing safe reversible metabolic suppression for years at a time in healthy humans remains unsolved. It may be solvable. It is not solved yet. The question of reproduction in space has barely been studied. No human being has ever conceived a child in microgravity or in the radiation environment of deep space. Animal studies suggest that mammalian embryonic development is disrupted by microgravity in ways that have serious implications. For a multi-generational interstellar voyage, a journey so long that the crew who launched would not be the crew who arrived, the question of whether human reproduction even functions normally in deep space is not academic. It is foundational, and no one knows the answer. Sending human beings to Proxima Centauri without solving these biological problems first is like planning a cross-country drive and forgetting to bring food and water. The vehicle might work perfectly. The route might be flawlessly planned. The destination might be real and reachable, but the people inside would not make it. So if humans cannot get there, is there anything else of ours that has or will? The answer will change the way travel means anything at all. In 2016, astronomers at the European Southern Observatory announced something that stopped conversations in physics departments, biology labs and philosophy seminars simultaneously. Using the radial velocity method, detecting the tiny gravitational wobble a planet induces in its host star as it orbits, they confirmed the existence of a planet orbiting Proxima Centauri. They named it Proxima b. The numbers were striking from the first announcement. Proxima b has a minimum mass of approximately 1.27 times the mass of Earth, making it by planetary classification standards a rocky terrestrial world rather than a gas giant. More importantly, it orbits within the habitable zone of its star. the range of distances at which liquid water could theoretically exist on a planetary surface given the right atmospheric conditions. The orbital period is just 11.2 days a year on Proxima b, is less than 2 Earth weeks, a consequence of how close it sits to its dim, cool host star. But that proximity is precisely what puts it in the habitable zone. Proxima Centauri is a red dwarf producing only a small fraction of the energy our Sun generates, so a planet must orbit very close to receive enough warmth. Liquid water. That phrase carries enormous weight in astrobiology, not because water is inherently special in some mystical sense, but because every living thing ever discovered or studied on Earth, every bacterium, every fungus, every plant, every animal, every extremophile, thriving in boiling volcanic vents or Antarctic ice sheets requires liquid water at some stage of its existence. Water is the universal solvent of biochemistry as life has expressed it on this planet. Finding a world where liquid water could theoretically pool on a surface is not confirmation of life. It is confirmation that the first basic condition has been met. It is finding out that the kitchen has a stove before asking whether anyone is cooking. The question of whether Proxima b actually has liquid water or an atmosphere capable of sustaining it, or anything resembling the conditions life requires, that question is where the straightforward excitement runs into serious complication. Proxima Centauri is a red dwarf star. Red dwarfs are the most common type of star in the galaxy, smaller and cooler than our Sun, burning their fuel so slowly that they will outlive Sun-like stars by trillions of years. In many respects, they seem like ideal hosts for habitable planets. But they have a problem that only became fully apparent as astronomers studied them more carefully. Red dwarfs are violent. Proxima Centauri, in particular, is classified as a flare star, a star that regularly, unpredictably and with very little warning, releases enormous bursts of ultraviolet radiation and X-rays. These flares are not modest events. In 2017, astronomers recorded a flare from Proxima Centauri that briefly increased its ultraviolet output by a factor of roughly 1,000. In a matter of minutes, the radiation environment around any orbiting planet changed catastrophically. Earth is protected from such events by its magnetic field, the planet's internal dynamo, generating an invisible shield that deflects charged particles and high-energy radiation away from the surface. Strip that protection away and even a modest solar flare would begin stripping the atmosphere and irradiating the surface within geological timescales. Proxima b's situation is precarious in precisely this way. Because it orbits so close to its star, tidal forces have almost certainly locked one hemisphere permanently facing Proxima Centauri, the same way the Moon always shows the same face to Earth. Tidally locked planets have unusual atmospheric dynamics. More critically, a tidally locked planet in such close proximity to a violent flare star without confirmed magnetic shielding faces a radiation environment that could strip its atmosphere entirely over millions of years, or sterilize its surface repeatedly, even if the atmosphere survives. This does not make Proxima b lifeless by definition. Life has survived extraordinary conditions on Earth. Organisms living in highly irradiated environments in complete darkness under crushing pressures, in conditions that would kill a human being instantly. The universe has repeatedly demonstrated that life's tolerance for hostile environments exceeds what intuition suggests. Underground oceans, protected by kilometers of rock, would be shielded from even the most violent surface radiation. Chemical processes that do not depend on sunlight at all could theoretically persist in subsurface environments, regardless of what happens above. The surface might be hostile. Below the surface is a different question, and one that cannot currently be answered from Earth. Then, in 2023, new data complicated the picture further in an interesting direction. Analysis of Proxima Centauri's light passing around and through the vicinity of Proxima b suggested possible signatures consistent with the presence of an atmosphere. The findings were not conclusive. The methodology is indirect, the uncertainties are large, and the scientific community has responded with appropriate caution. But the suggestion that Proxima b might retain some atmospheric envelope, despite its proximity to a flare star, and despite theoretical models that predict atmospheric erosion, reopens questions that seem to be closing. If it has an atmosphere, even a thin one, even one chemically unlike Earth's, the implications cascade outward immediately. An atmosphere means pressure. Pressure means the possibility of liquid water at the surface. Liquid water at the surface means the first condition for life as understood from Earth is met. And if that chain holds, then Proxima b is not just the closest exoplanet. It is the closest potentially habitable world, 4.24 light-years away, right there in cosmic terms just across the street, which is where the Fermi paradox enters quietly and uncomfortably. Enrico Fermi, the physicist, asked the question in 1950, simply at lunch, almost casually. If the universe is this large and this old, and if life is not impossibly rare, where is everybody? The galaxy is approximately 13 billion years old. Civilizations that arose even 1 billion years before humanity would have had time at even modest interstellar travel speeds to spread across the entire Milky Way many times over. The silence is strange. It requires explanation. Either life is extraordinarily rare, rarer than the optimistic numbers suggest, or something prevents civilizations from expanding indefinitely, or they exist and are simply not communicating in ways detectable from Earth. None of these options is comfortable. If Proxima b has life, if there are organisms of any kind on or beneath that battered radiation-soaked world, 4.24 light-years away, the silence from that direction becomes part of the paradox. Why nothing? Why no signal? No artifact? No evidence of any kind of organized process beyond the natural? And if Proxima b is barren, if the habitable zone placement and the possible atmosphere and the Earth-like mass all amount to nothing because the radiation environment never permitted complexity to arise, then the paradox tightens. Further, because Earth sits in the same galaxy around a more stable star with better shielding, with more favourable conditions in almost every measurable way, and it produced everything from bacteria to Bach. Why here and not there? What exactly is the variable that made Earth different? These are not rhetorical questions. They are among the most important questions in science, questions that the existence of Proxima b forces into sharper focus than any theoretical argument alone could manage. The planet is real, the distance is real, the uncertainty is real, and the stakes of resolving that uncertainty, of finding out whether the nearest potentially habitable world is inhabited or empty, carry implications that reach far beyond astronomy into philosophy, religion, and the deepest questions about what life is and what it means that it exists at all. Humanity does not yet know whether anyone is home on Proxima b. That answer may come from a telescope long before any spacecraft arrives. It may never come. But one thing is already established without ambiguity. This is the nearest target, the most real candidate, the most plausible address in the cosmic directory. And the distance standing between humanity and that answer is reshaping the entire scope of what civilization considers worth attempting. At this point, the question is no longer, how hard is it? But why do we still want to go, knowing full well the cost? What follows will offer an answer that nobody sees coming. The greatest journey in human history did not begin with a rocket. It did not begin with a control room, a countdown, a billion-dollar launch vehicle, or a government program. It began with a raft. 4,000 years ago, long before any written record of the voyage existed, human beings climbed onto wooden outrigger canoes in the Western Pacific and sailed east into open ocean. They had no maps, no compass, no GPS, no satellite imagery of what lay ahead, no radio contact with anyone behind them, no guarantee that land existed in any direction beyond the water visible from the bow. What they had was a detailed, intimate knowledge of the stars, their positions, their seasonal movements, their relationships to one another across the dome of the sky, and a set of skills for reading ocean swells, wind patterns, cloud formations, and the behavior of birds that represented generations of accumulated knowledge passed through oral tradition. With these tools and with a willingness to sail into genuine uncertainty, the Polynesian navigators settled the vast triangle of the Pacific Ocean from Hawaii in the north to New Zealand in the southwest to Easter Island in the east. They found islands scattered across the largest ocean on Earth, separated by thousands of kilometers of open water, navigating with a precision that modern GPS-equipped researchers have spent decades trying to fully understand. No one told them there was land out there. They went anyway. This pattern repeats across the entire span of human expansion in ways too consistent to be coincidence. In 1492, Christopher Columbus sailed west from the Canary Islands into the Atlantic Ocean. The educated opinion of his era was not that the Earth was flat, that is a myth. Educated Europeans of the 15th century understood very well that the planet was spherical. The genuine uncertainty was what lay in the water between Europe and Asia, and whether a ship provisioned for a finite journey could survive whatever it was. Many people believed the ocean was simply too vast to cross with the technology available. Some believed in sea monsters. Some believed in navigation hazards that could not be predicted or survived. Columbus and his crew went anyway, not because they were certain of success, but because the alternative, staying on the shore and never knowing, was something certain kinds of minds find genuinely intolerable. Then the atmosphere. For centuries, the idea that a human being could survive above the clouds was not a technical problem. It was not considered a problem at all, because it was not considered possible. The air was understood to thin with altitude. The summit of Mont Blanc at 4,807 meters was considered a limit beyond which human physiology could not function. And then Orville and Wilbur Wright flew at Kitty Hawk in 1903. And within 66 years, Neil Armstrong stepped onto the surface of the moon. 66 years from the first powered flight to leaving footprints on another world. By any historical measure, that is not a slow rate of progress. That is barely 2 human generations. Then gravity itself, the force that held every living thing on Earth's surface for the entirety of biological history, the force that shaped every aspect of vertebrate anatomy, the force that for most of human existence defined an absolute ceiling above which nothing made by human hands could travel. And then on the 4th of October, 1957, Sputnik crossed the Terminator into orbital velocity and the ceiling dissolved. The pattern is not random. Something in human cognition treats the existence of an unreached boundary as an active problem requiring resolution. Carl Sagan described it as humanity being wanderers by nature, and while that phrase has been repeated so often it risks becoming decorative, what he was pointing to was not poetry. It was evolutionary biology, the human brain, shaped by natural selection across hundreds of thousands of years of migration of following prey across continents, of moving into new environments when old ones became depleted or dangerous, carries a deep architectural bias toward novelty-seeking and territorial expansion. Populations that stayed put when resources became scarce died. Populations that moved found new resources and survived. Curiosity and the compulsion to cross the next ridge are not personality quirks. They are survival mechanisms encoded over geological timescales. But there is a darker version of the same argument, one that removes the romance and replaces it with something more urgent. If humanity does not extend beyond Earth and Earth encounters a sufficiently catastrophic event, an asteroid large enough to trigger a mass extinction, a supervolcanic eruption of the scale that produced the Siberian traps 252 million years ago and eliminated over 90% of marine species, a runaway climate shift, a pandemic of a virulence not yet encountered, then everything ends. Not just human civilization, everything. 4 billion years of biological evolution on this planet, from the first self-replicating molecules in warm, shallow seas to the entire current complexity of the biosphere, concludes without continuation, no record, no survivors, no second chance. The universe does not preserve backup copies. This is not a theoretical concern dressed in dramatic language. It is the straightforward implication of all life existing on a single planet in a universe that regularly and indifferently produces extinction-level events. The fossil record is explicit. Life on Earth has been nearly wiped out 5 times in the last 500 million years alone. The 6th mass extinction is a topic of active scientific debate regarding whether it is already underway. A civilization that has the cognitive capacity to understand this risk and chooses not to act on it is making a decision, not a neutral one. So when the question is asked, why do humans want to go to Pluto, to Proxima Centauri, to the stars, when the cost is so enormous and the returns so uncertain, the honest answer has 2 layers. One is the deeply human, almost irrational compulsion to see what is on the other side of the horizon. A compulsion so consistent across cultures and centuries that it looks less like a choice and more like a defining characteristic of the horizon, species. The other is colder and more logical. A civilization confined to one planet is a civilization with a single point of failure, and the universe has demonstrated repeatedly that it will eventually exploit exactly that kind of vulnerability. Do you think the drive to explore is genuinely encoded in human DNA, a real biological imperative? Or is it a story humanity tells itself to justify behavior that is at its core just restless and expensive risk-taking? But wanting to go, there is one thing. Whether humanity can actually go in the near future is another. And what is happening right now will change that answer faster than anyone predicted. The conversation about interstellar travel, about Proxima Centauri, about the physics of reaching another star system, it can start to feel like philosophy, like an intellectual exercise conducted at a comfortable distance from anything that might actually happen within a human lifetime. That impression is wrong. The infrastructure for the next phase of human space expansion is being built right now, with real budgets, real contracts, and real launch schedules, at a pace that would have seemed implausibly optimistic a decade ago. Start with the foundation that already exists. NASA's Artemis program returned humans to lunar orbit for the first time since 1972 and is working towards sustained human presence on and around the Moon. The Lunar Gateway, a small space station planned for lunar orbit, is designed not as a destination in itself, but as a staging point, a refueling and resupply node for missions deeper into the solar system. The explicit architecture of Artemis treats the Moon as a proving ground for the technologies and operational procedures that crewed missions to Mars will require. Mars, in turn, is understood within NASA's long-range planning as a proving ground for deeper missions. This is not a program for going to the Moon. It is a program for learning how to leave the inner solar system with people aboard. SpaceX's Starship changes the economic equation of space access in ways that, if the vehicle achieves its design goals, will be genuinely transformative. The space shuttle cost approximately $54,000 per kilogram to deliver payload to low Earth orbit. Starship, fully reusable and designed for rapid turnaround between flights, in the way commercial aircraft are reused, is targeting a cost somewhere in the range of $100 per kilogram. That is not an incremental improvement. It is a reduction by a factor of 500. Launch cost is one of the most fundamental constraints on what space missions are feasible. It determines spacecraft size, mission frequency, and the volume of equipment and supplies that can be sent anywhere. Reducing it by 500 times does not make a few more missions possible. It changes which missions are thinkable at all. On the propulsion side, DARPA and NASA are jointly funding research into nuclear fusion propulsion, through programs including DARPA's demonstration rocket for Agile Cislunar Operations Initiative and NASA's investments in advanced propulsion concept. Fusion propulsion, if achievable, would offer a specific impulse, a measure of propellant efficiency dramatically higher than chemical rockets, potentially enabling transit times to Pluto in the range of 2 to 3 years rather than 9. 2 to 3 years. For a destination that required almost a decade with the best chemical propulsion ever flown. The difference between 9 years and 2 years is not just convenience. It is the difference between a mission profile that kills the crew through accumulated radiation and biological deterioration and one that might not. Breakthrough Starshot continues its development work. The engineering challenges laser array power, sail material survival in the interstellar medium miniaturized instrument packages, capable of operating at 20% of light speed and transmitting data back across 4 light years, are being worked on by research teams at multiple institutions. The project's timeline targets a first-generation demonstration before 2050. Whether that target holds depends on funding, on materials science breakthroughs, on international cooperation. But the project exists, it is funded, and people are working on it every day. And then there is the telescope question, which produces one of the more satisfying ironies in this entire story. The James Webb Space Telescope, despite being the most powerful space observatory ever built, cannot directly image Proxima b. The orbital geometry is unfavourable. The planet transits at an angle relative to Webb's line of sight that makes direct observation of its atmosphere essentially impossible with Webb's instrument configuration. But the next generation of ground-based observatories is designed with exactly this kind of target in mind. The extremely large telescope, currently under construction by the European Southern Observatory in the Atacama Desert in Chile, will have a primary mirror 39 meters in diameter, nearly 4 times the diameter of any existing ground-based telescope, When it begins operations expected in the late 2020s, it will be capable of directly imaging exoplanets and analysing their atmospheric chemistry through spectroscopy. The Giant Magellan Telescope and the 30-metre telescope represent parallel efforts toward the same capability. Within 10 to 20 years, these instruments may be able to detect biosignatures, chemical signatures, in Proxima B's atmosphere, inconsistent with purely geological or chemical processes, consistent with biological activity, without sending anything there at all. Ironically, the fastest way to find out whether anyone is home at Proxima B may not be to fly there. It may be to sit on Earth and look through a sufficiently powerful telescope. But of all the plans currently in development, there is one that scientists talk about the least yet, which is quietly becoming the most compelling candidate of all, and it is not a rocket. The solution nobody is talking about does not involve thrust. It does not involve fuel-mass ratios or gravity assists or laser arrays or antimatter. It involves something so simple and so strange that the first instinct is to dismiss it as metaphor rather than engineering. Information travels at the speed of light. That sentence contains more practical consequence than it might appear to. A rocket carrying human bodies to Proxima Centauri faces every obstacle catalogued across this entire journey. Radiation, biological deterioration, psychological collapse, fuel requirements that strain the limits of physical possibility. But information, a signal, a transmission, a precisely encoded sequence of data beamed outward from Earth faces none of those obstacles. It does not atrophy. It does not go mad in a metal box. It does not require oxygen or food or shielding from cosmic rays. It travels at 299,792 kilometers per second, and it arrives at Proxima Centauri in 4 years and 89 days, no matter what the signal contains. What could a signal contain? Here is where the idea stops being poetic and starts being science. Researchers at Harvard, MIT, and a growing number of institutions working at the intersection of synthetic biology, information theory, and astrobiology have been exploring a concept, sometimes called directed panspermia, by information or more, colloquially digital seeding. The premise is straightforward enough to state in a sentence. Instead of sending physical life to another world, send the instructions for building it. The complete human genome, the 3 billion base pairs of DNA that encode the biological architecture of a human being, can be represented as a digital file of approximately 1.5 gigabytes. That is smaller than a high-definition film. A radio transmission carrying that information beamed at Proxima Centauri would arrive in 4.24 years. The body does not travel. The blueprint does. The obvious objection is that a blueprint is useless without a factory to read it, and that is precisely where the second half of the idea comes in. Robotic precursor missions physically launch spacecraft smaller and lighter than anything carrying a human crew designed not to carry life but to build infrastructure would arrive first. Over decades or centuries, they would construct the receiving apparatus, fabrication systems, biological printers, energy collection, hardware, whatever the destination environment requires. Then, when the infrastructure is ready, the signal arrives, and the blueprint is read. Synthetic biology, the engineering of biological systems from chemical components, according to a genetic specification, has already demonstrated that simple organisms can be assembled from synthesized DNA sequences in laboratory conditions. Craig Venter's team at the Craig Venter Institute created the first synthetic bacterial cell in 2010, assembling its entire genome from chemically manufactured fragments. That was a bacterium. The gap between a bacterium and a human being is vast, but the principle that life can be instantiated from information rather than transmitted as physical matter is no longer hypothetical. It is a demonstrated fact at the microbial scale. What the Harvard and MIT researchers are working toward is not science fiction. It is a research roadmap with funding, publications, and incremental milestones. The challenges are enormous, keeping a robotic constructor functional across interstellar distances, solving the problem of biological printing at the complexity of multicellular organisms, ensuring the fidelity of transmitted genetic information across 4 light-years of signal. Degradation. None of these are solved. But none of them violate physics. That distinction matters enormously. And then there is the version that does not involve biology at all. An artificial intelligence carrying the complete accumulated knowledge of human civilization. Every book ever written, every scientific finding ever recorded, every artistic work ever digitized, every language, every cultural tradition, representable in information, weighs nothing. It requires no life support. It cannot get cancer from cosmic radiation. It does not need to eat or breathe or maintain bone density or manage its psychology through 2 decades of isolation. A sufficiently capable AI launched aboard a Breakthrough Starshot-style probe, or even transmitted as a signal to pre-built hardware at the destination, could arrive at Proxima Centauri and begin doing something recognizable as exploration, observing, measuring, recording, analyzing, and transmitting findings back to Earth. It could characterize Proxima B's atmosphere in detail. It could identify whether chemical signatures of biology are present. It could potentially do everything a human scientist would do upon arrival, without any of the biological constraints that make human arrival so difficult. This raises a question that science cannot answer, but that philosophy cannot avoid. If an AI carrying the sum of human knowledge reaches Proxima Centauri, explores the system, and transmits its findings back to Earth, has humanity reached Proxima Centauri? Most people's first instinct is to say no. It is a machine. It is not a person. The experience of standing on an alien world, of breathing foreign air, of feeling the gravity of another star's planet beneath your feet, none of that is transmitted. The data comes back. The wonder does not. But push the question one step further and the ground becomes less stable. If a perfect, complete map of your brain, every neural connection, every synaptic weight, every memory, every pattern of cognition that constitutes your personality, your fears, your attachments, your way of being in the world, were encoded into a signal and transmitted to Proxima B, and at the other end, A, the substrate received that signal and instantiated it completely, running your cognitive architecture in full fidelity, would that be you? Materialist philosophy says yes. You are not your specific carbon atoms, which replace themselves continuously throughout your life. You are the pattern. The pattern is the person. If the pattern is preserved and instantiated correctly, the person is there. The continuity of experience would be unbroken from the perspective of whoever wakes up on Proxima B, because every memory of being you would be intact, including the memory of deciding to make the journey. Other frameworks say no, that the person who arrives is a copy, that the original still on Earth or dead in transit is not the same individual as the reconstruction. That something, essential consciousness, subjective experience, whatever makes awareness feel like something from the inside, does not survive the transmission in any meaningful sense. That what arrives at Proxima B is an elaborate replica convinced of its own continuity, but not actually continuous with the person who encoded it. This is not a question physics can resolve, and it may be within the next century the most practically important philosophical question humanity has ever asked. Because if the answer is yes, if information-based transmission of human identity is genuinely possible and genuinely equivalent to physical travel, then the distance to Proxima Centauri stops being a barrier and becomes a 4-year delay. If the answer is no, then the only version of humanity that counts is the biological one. And all the obstacles come rushing back. But all of this, the rockets, the robots, the digital seeds, the AI explorers, the transmitted minds, are all skipping past a foundational truth that almost nobody is willing to face directly. And that is the real reveal of everything that follows. 5 billion years, that is how long the sun has left before the physics of stellar evolution catches up with it. The process is already underway, has been since the sun ignited 4.6 billion years ago, and it proceeds according to equations that admit no uncertainty about the outcome. As the sun fuses hydrogen into helium in its core, the core gradually contracts and heats. The outer layers respond by expanding. The luminosity increases slowly, steadily. Measurably, the sun today is approximately 30% brighter than it was when life first appeared on Earth. And that trend continues without pause. In roughly 5 billion years, the sun will have exhausted the hydrogen in its core entirely. The transition will not be gradual in astronomical terms. The core will collapse. The outer layers will balloon outward into a red giant, expanding past the orbit of Mercury, past the orbit of Venus, almost certainly swallowing Earth entirely. The oceans will boil away long before the surface contact. The atmosphere will be stripped. The rock itself will eventually melt into the sun's expanding envelope. This is not a theory. It is not a model with significant uncertainty. It is a prediction derived from stellar physics verified across thousands of observed stars at various stages of the same process. Red giant expansion is not a possible future for the Sunday. It is the certain one. 5 billion years sounds like an enormous amount of time. Long enough certainly to solve the engineering problems of interstellar travel. Long enough apparently to relax. But that is the wrong frame entirely, because 5 billion years is not the operative constraint. 4.5 billion years from now, the Milky Way and the Andromeda Galaxy will collide. They are already approaching each other at approximately 110 kilometers per second. The merger will unfold over hundreds of millions of years, the two galactic structures interpenetrating and distorting stellar populations, mixing spiral arms, shredding and reforming into something new. Individual stars are unlikely to physically collide. The distances between them within each galaxy are too vast for direct contact, but the gravitational restructuring of the entire galactic environment will be profound. Stellar orbits will be disrupted. The Sun and its planets may be flung into entirely new trajectories within the merged galaxy. The night sky will transform beyond recognition. Whether the solar system remains in a stable, life-friendly region of the resulting structure is genuinely uncertain. 4.5 billion years. Still a number so large it feels academic. Make it smaller. In approximately 600 million years, a process already underway will reach a threshold with consequences for every living thing on Earth's surface. The Sun's gradually increasing luminosity will heat the planet to the point where silicate weathering the chemical process by which carbon dioxide is drawn out of the atmosphere and locked into rock accelerates beyond the rate at which volcanoes can replenish it. Carbon dioxide concentrations will fall below the minimum threshold at which photosynthesis can sustain plant life. When plants go, everything built on them goes. The entire food web constructed on photosynthetic primary production, which is essentially every food web on Earth's land surface, collapses. 600 million years sounds distant. It is roughly the same span of time that has elapsed since the Cambrian explosion. When complex multicellular life first diversified explosively in Earth's oceans, everything since the first trilobite, every fish, every amphibian, every dinosaur, every mammal, every human civilization happened inside a window of time comparable to what remains before the photosynthetic collapse. That is not forever. That is a finite window already spending down. Make it smaller still. Mass extinction events have struck Earth 5 times in the last 500 million years. The Ordovician extinction, the late Devonian extinction, the Permian extinction, the largest of all, which eliminated over 90% of marine species and over 70% of terrestrial vertebrate species approximately 252 million years ago. The Triassic extinction, the Cretaceous extinction 66 million years ago, which ended the non-avian dinosaurs and cleared the ecological stage for the mammals who eventually produced humanity. 5 catastrophic resets in 500 million years, roughly 1 every 100 million years on average. Though the distribution is not uniform and the causes vary, asteroid impacts, volcanic outgassing on a planetary scale, oceanic chemistry shifts, combinations of factors still actively debated. The 6th mass extinction is no longer a future scenario in some scientific conversations. It is a present condition. The question being posed here is not whether Earth will eventually become uninhabitable. It will. Not whether large-scale catastrophes will occur before that terminal timeline. They will. The question is this: how much time does a civilization actually have to transition from a single planet species to something more distributed, more resilient, more capable of surviving what the universe reliably delivers to any fixed address in the cosmos? The honest answer is not as much as the 5 billion year headline implies. Not close. Every decade without meaningful investment in the technologies that could extend human presence beyond Earth is not a neutral decade. It is a decade subtracted from a window that biology, geology, and astrophysics are all actively closing at different rates on different timescales, but closing nonetheless. The asteroid that ended the Cretaceous gave no warning sufficient for any response. The Permian extinction unfolded over a span geologically brief, but still far longer than human civilization has existed. The universe does not schedule its catastrophes for convenient moments. It does not wait for the engineering to be finished. This is not a call for panic. It is a call for proportion. The scale of the problem reaching Pluto, reaching Proxima, becoming capable of surviving beyond Earth is so large that it is easy to treat it as a concern for future generations, for future technology, for a future humanity that will be cleverer and better resourced than the present one. But every generation that has ever existed has told itself exactly this, in slightly different language about slightly different problems. And the window does not care about the reasoning. It closes regardless of the justification offered for waiting. Luai ngui honko hang tinam de huanthiant kungay. That framing billions of years comfortable distance someone else's problem is precisely the framing that the physics refuses to support. The relevant timescales are not the sun's remaining lifetime. They are the intervals between the last 5 mass extinctions, which average roughly 100 million years. They are the 600 million years before the photosynthetic baseline of terrestrial life fails. They are the time frame in which a species goes from powered flight to the moon in 66 years, and then, if the trajectory stalls fails, to take the next step for generations because the urgency felt distant. If you knew confirmed certain written into the physics that Earth had a finite operating period remaining, and that the window for becoming something more than a single point of failure civilization was measurable in geological rather than infinite time, would that change the weight of the question? Would Pluto feel less like a curiosity and more like a rehearsal? Would Proxima Centauri feel less like an aspiration and more like a necessity? Or would it make right now feel more urgent than any destination? This planet, this atmosphere, this precise and unrepeatable arrangement of water and light and biological complexity that took 4 billion years to produce and make the impulse to leave feel almost ungrateful. Both reactions are honest. Neither cancels the other out, but one of them the universe will register and one it will not. Everything examined here, Pluto and its 9-year crossing Proxima and its 40 trillion kilometre silence, the rockets and the robots and the transmitted minds and the closing windows of deep time has been building toward a final perspective, one that does not summarise what came before it, one that makes every scale considered so far collapse into a single vertiginous point, and it is stranger and quieter and more unsettling than any number in this story. The question asked at the very beginning of this journey was how hard is it really to reach Pluto and Proxima Centauri? And the answer built up across everything that followed seemed clear enough. 9 years and 5 months to a dwarf planet at the edge of the solar system, 73,000 years to the nearest star at current speeds, radiation that would kill a crew before arrival, fuel requirements that defy practical engineering, biology that dismantles itself in the absence of gravity, psychology that collapses under decades of isolation. The answer seemed to be very hard. Nearly impossible with what humanity currently has. But that was the wrong question. The right question is this: how hard is it to survive without going? Sit with that inversion for a moment, because it changes everything that came before it. Every obstacle examined the distances, the fuel mathematics, the radiation, the biological fragility, the engineering gaps. All of it was framed as the difficulty of reaching somewhere, as if staying here were the default, the safe choice, the option that costs nothing. But the preceding examination of geological timescales of mass extinctions arriving without scheduling, of the sun's certain expansion, of the Milky Way's eventual collision with Andromeda, all of that reframes the difficulty. The question is not whether leaving is hard. The question is whether staying indefinitely on a single planet in a universe that operates at these scales is survivable at all. It is not, which means the obstacles are not reasons to stop. They are the exact shape of the problem that needs solving. And while that problem remains unsolved, something extraordinary is already out there. Voyager 1 was launched on the 5th of September 1977. That is 47 years ago. It has never stopped. It has never slowed beyond the minimal deceleration imposed by the sun's gravitational pull, which at this distance has become nearly negligible. Right now, as this is being read, Voyager 1 is approximately 24 billion kilometers from Earth, farther from home than any object humanity has ever made. In 2012, it crossed the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium, the thin gas and magnetic fields that fill the space between star systems. That crossing made Voyager 1 the first human-made object to enter interstellar space, not metaphorically, literally. It is out there between the stars right now. It will approach the next star on its trajectory, a dim red dwarf catalogued as AC+, 79, 3,888 in approximately 40,000 years. 40,000 years of silent travel, no engine firing, no course correction, just inertia, carrying a machine built by human hands through the darkness between stars. By then, whatever humanity has become, or whatever has replaced it, or whatever has been built from its remains, will either have developed the means to receive what Voyager 1 represents, or will not exist at all to notice its passing. But here is what Voyager 1 is carrying, and this is where the story stops being about engineering. Bolted to its exterior is a 12-inch gold-plated copper disc, the Golden Record. On it, 115 images encoded in analog form, photographs of Earth, of humans, of mathematical diagrams explaining how to decode the disc itself. 116 distinct sounds, including wind and rain and surf. The sound of a mother's first words to a newborn child, the sound of a chimpanzee, the sound of a pulsar, greetings in 55 human languages, including ancient Sumerian and Aramaic. 90 minutes of music, Bach, Beethoven, Blind, Willie Johnson, Chuck Berry, Azerbaijani folk song, Indian classical raga, Peruvian panpipes, and instructions expressed in the universal language of mathematics and pulsar positions, explaining where this object came from, when it was launched, and how to play the disc should any intelligence ever find it. A message sent into the void, addressed to no one specific, expected to be found by no one in particular within any predictable time frame if ever, and yet sent anyway. Because the people who built it, Carl Sagan and Anne Druyan, and the team around them, understood something instinctively that the entire preceding examination has been building toward from a different angle, that the act of sending matters, that reaching out into silence without guarantee of response is not futility. It is the only honest expression of what a conscious species is. Now, the final scale, Proxima Centauri, is 4.24 light-years from Earth. That number has appeared throughout this story as the definition of a vast distance, the impossible gap the wall at the edge of ambition. And it is vast by every human measure ever devised. But the observable universe is 93 billion light-years in diameter. Do the arithmetic. 4.2. 4 light-years, the distance to the nearest star, the target of humanity's most ambitious interstellar proposals. The subject of this entire exploration represents 0.00000000000, 5% of the observable universe's diameter, written with the zeros present 0.000000005. Proxima Centauri, the star that took an entire story to establish as almost unreachable, sits at a distance that is relative to the full scale of what exists, essentially zero. A rounding error on a rounding error. The Milky Way galaxy contains an estimated 400 billion stars. It spans approximately 100,000 light-years across. That galaxy, every star ever visible to the naked eye from Earth, every star system anyone has ever named or catalogued, the entire stage on which all of human astronomy has been conducted, occupies a single small region within a universe, containing an estimated 2 trillion galaxies. 2 trillion. The Milky Way is one of them. 1 point among 2 trillion, most of which are receding from us so rapidly that no spacecraft, no signal, no information of any kind will ever bridge the distance to them. They are already beyond reach, not because of engineering limitations, but because the expansion of spacetime itself carries them away faster than light can cross the growing gap. And the observable universe, the 93 billion light-year sphere within which any observation or communication is theoretically possible, is itself only the portion of the total universe from which light has had time to reach Earth since the Big Bang. The actual universe almost certainly extends beyond the observable horizon by how much nobody knows. Current cosmological models suggest the total universe may be vastly larger than what can be seen, perhaps infinitely so. The observable universe is not the universe. It is the tiny circle of lamplight that 13.8 billion years of light travel time has illuminated around a single point in space. Humanity is standing on a pale blue dot, looking toward a star 4.24 light-years away, calling that the most ambitious target ever considered. The universe is not cruel about this. It is not designed to humiliate or discourage. It simply is what it is, ancient and enormous and indifferent to the scale at which any particular species is currently operating. The silence that stretches in every direction from Earth is not hostile. It is patient. It has been waiting for complex matter to organize itself into something curious for billions of years, and it will wait considerably longer without complaint. But it will not wait in the sense of holding the door open. It does not preserve opportunities indefinitely. Windows close on timescales ranging from a human lifetime to a geological epoch to the lifespan of a star. The universe is silent and patient, and it is watching in whatever sense an unconscious cosmos can watch. To see whether the species that built the golden record and launched New Horizons and calculated the orbit of Proxima b with enough precision to name its potential habitable zone, whether that species has the courage to actually begin. Not to complete, not to solve everything first, not to wait until the engineering is finished and the biology is solved and the philosophy of mind has settled the question of whether a transmitted consciousness is still a person. Just to begin, to treat the distance not as a wall but as a problem, to keep sending, to keep looking, to stay curious past the point where curiosity is comfortable. If this story made you look up at the night sky tonight and feel something you do not have an exact word for, that is not the end of anything. That is the beginning. Subscribe so you do not miss what comes next, where we will go deeper into the dark regions that even light has never touched.